Record. Thanks for reminding me. All right, I've do the record and share the screen. Okay. So can you see the presentation here?
Yes.
Okay, good. So we talk about the kind of generic process for the additive manufacturing, and we have gone through some of these aspects, like how to design for the. I don't think we have covered this. Actually, we just talked about this design aspects. Let me share the other slides instead of this. Okay. Yeah, this one's correct. So we talk about some aspects of the design in the additive manufacturing, specifically how to convert your CAD file into a kind of those mesh file like STL, right? And how can we generate the each layers through the STL file? And what does STL file look like? What's the information inside the file? And I think we are around here, right? The support, yeah, right? So basically, many of the process require supports like including those fuse deposition modeling and stereolithography, and also some powder bed process, as well as the direct energy deposition. So many of them, they all require support material because for some of these structures, overhanging, floating, sailing, unstable, or this base support, they require the printing of support material. So that's why before this part could be manufactured using additive manufacturing, the software need to generate those support material, support structures first. All right. And then what's the next? That is the slicing and the path planning, right? So basically, you need to generate the outer contour and also the infill. And here shows a, I would say, more complex examples that how the slicing will look like. And you can see if we check one layer like this one, right? You can see some regions in different colors. One's the blue region and another one's the red region. And the blue one will be the one for the part. And the red region actually is the one for the support material, right? So during the printing process, all these regions will be processed, and some of the material will be accumulated here. And sometimes the support material and the building material are the same material, but sometimes they are different. And that gives the both limitation and opportunities, like we discussed last time. I mean, on Tuesday's class. In Tuesday's class, we talk about those mechanisms, right? And so how to realize a motion without assembly. Then we can kind of print some salutable support material. And then after the post-processing, all the material salutable material will be washed away. And then you have a totally functional part with all the motion realized. So that is a kind of the good side for printing support material. But there are also bad side. Sorry. First of all, it wastes material, right? And it wastes time. You have to consume the material and time to generate a support, right? And also sometimes it's just hard to do some post-processing to remove the support material. And sometimes the removal of the supporting material will kind of affect the surface finishing. So you have to do actual work to make your part ready to use, right? That is the, I would say, the downside for printing support material. And there are some researchers try to figure out a way to avoid support material, and I will introduce one of the, some of them, some of these efforts, and in the later lectures. All right, but even after you set up all the slicing, I mean each layers and also the tool path, you still need to set up the machine, right? Including some aspects like the energy source, what's the timing, right? Material constraints, and you have to kind of home your machine and warm it up. For some of the process like the fuse deposition modeling, you have to heat up your nozzle, right? And also the selective laser sintering, right? You also need to warm up your machine such that it can be ready for you to generate the 3D objects. So that's some pre-manufacturing work you need to do before the printing can be actually done. And then the fifth step is to actually build the 3D object you are gonna you want to print, you want to manufacture, right? And most of them, they are the automated process. But there are also some iterative process, right? You have to for some of those hybrid printing process, the additive manufacturing system will generate the rough shape, and then the subtractive system, like those 5-axis CNC machine system will fine-tune the part to have a better surface finishing, right? So it could be an iterative process. And but the thing is, there's little human interaction. So basically, especially for some of the process like fuse deposition modeling, basically the user has nothing to do when they click on the print, right? And also there's no feedback control, right? Basically, if there's one layer has problems, then the whole printing will be failure. So how to kind of improve this kind of reliability during the printing process, that's also a research direction. All right. Then the step 6 is some post-processing, right? So as I mentioned, you probably need to remove all the support material and also clean up the building material. For example, some those liquid-based method like stereolithography, you need to wash. You need to wash the part you printed, and also remove the support material. So that could be some safety issues, like if the material is toxic or hazard, you need to be careful, right? Some necessary protection need to be is required to protect the user to touch those parts, right? And some of the process requires high temperature, right? For example, like what we discussed, those binder-based metal printing, right? So the post-processing will be a heat treatment, right? So you have to have environment with very high temperature. And also for the powder bed metal printer, it has a very high power laser over there. So the safety is very important. People have to be trained to operate those systems. And well, that's all the issues need to be considered before 3D printing. I mean, additive manufacturing can be done, right? All right.
Do you know what the
yeah,
what the structure is on the left picture?
You mean this one, right?
Yes.
Let me. Okay, I have no laser pen. You mean this one, right?
Yes.
Okay, so these are, I would say that these are quite regular ones. Basically, it's all the like a truss structure, right? And also the layout of the patterns is quite regular. Basically, they just put everywhere they think is necessary to put this kind of structure. Actually, I don't know whether you have some chance to print using the stereolithography method. Actually, this is more suitable for the stereolithography SLA process. For printing FDM, it has different patterns. So that is the SLA kind of a, I mean, this structure is kind of more suitable for SLA process. But that's still a regular, I mean, quite regular printing, support material. Actually, there's some new development. They're trying to minimize this shape. Then the layout of the pattern, actually, they are quite irregular. And you can see some like those tree structure, right? And not like this, still quite, basically, these are some blocks, but consists of all the truss structure. But for what I mentioned, the advanced method, it's not like this. I can show you some examples in the future lectures.
Okay. Thank you.
Yeah. But the right one is the one for the fuse deposition modeling. This one's the typical printing structures for the fuse deposition modeling, but this one's for the SLA. All right. So also other possible post-processing will be the part finishing, polishing, sandpapering, or machining, right, as I mentioned. Or you can also paint your part, like this plain part you just get from your additive manufacturing system. You can just paint it, use the color you want. And also some over-curing, especially for the stereolithography-based method. You want to make sure your part is strong enough. Then there could be some over-curing process there. All right. And also coating and infiltration to strengthen the part. Basically, this kind of process may involve some chemical reaction over there using some solutions or some chemical stuff over there to kind of make your the original material become stronger. As you can see, with different additive manufacturing process, we have all the different applications, and some of them like this kind of food printing is kind of relatively, well, I would say is more like a demonstration instead of a practical application. But some of them I will see is quite practical, like the helmet and also the customized shoes. Actually, there are some products already there, like Nike and Adidas. They are kind of teaming up with some additive manufacturing companies and work on those customized kind of sports gears. And some emerging area like those bioprinting and drug printing, I would say, I mean, in the near future, hopefully there will be some breakthrough coming out. All right, and so we just did a kind of overview on the design and optimization aspects of additive manufacturing. So in the following few kind of lectures, I would like to introduce some examples or case studies in this area, such that you could have a better understanding for the design, optimization, modeling in additive manufacturing. Why we talk so much about this? Because compared to all other manufacturing process, the computational side is including modeling, optimization, and the simulation and so on and so forth are so important for additive manufacturing. And there are a lot of open questions need to be answered, because actually we discussed a lot in last lectures, the on-site lectures. So I would say it is good for us to kind of have an in-depth overview, kind of discussion in these sections. All right. Let's share another one for you. That is the, all right. So for the 3D content creation and editing, again, this is the generic process for the additive manufacturing. And well, if we talk about the design for additive manufacturing, actually that is kind of quite similar to what we usually call the design for manufacturing, right? So basically the design for manufacturing is kind of with certain manufacturing process, how you're gonna design your product, which can be successfully and efficiently manufactured using a certain manufacturing process, right? So you have to consider about the benefit and also the limitation when you choose one manufacturing process and when you do the design for it. So what will be the consideration for additive manufacturing process, right? And so, for example, like some manufacturing process like injection molding, and you have to have some understanding such that you could design your machine tool, and you could decide what kind of shape you can manufacture using such manufacturing process. And for additive manufacturing, it's just the same concept. Like, for example, like this one, if you want to machine it, then you need to think about, okay, whether these dimensions, I mean, these geometric features can be manufactured using machining, right? You have to think about whether the dimension of these features can be machined, right? For example, if this cavity or this one is too small and there's no way to put your tool there, then it is not manufacturable. So all these examples suggest when you have a certain manufacturing process, there are some limitations you need to consider about, such that the part you designed can be manufactured successfully. And as I mentioned, also the manufacturing process could bring you some opportunities. And that happens to additive manufacturing in both of them, all right? So like this one, right? The left one actually is the original design, which can be manufactured using other traditional manufacturing process. I would say probably some injection molding. I don't know. Yeah, right. So as you can see, it consists multiple parts, and it requires the screw, maybe glue to assemble all the parts together, right? And that is because that's the only way it can be manufactured using certain manufacturing process. But how about if we use additive manufacturing, right? Like the design shown here. Basically, in this design, a lot of parts are putting together, and there's no fastener over there, right? And obviously, it couldn't be manufactured using other manufacturing process. But how about additive manufacturing, right? So this definitely can be manufactured using additive manufacturing. And the benefit is you don't need the fasteners. You don't need to do the assemblies. And you can have the part, as a whole part without different assemblies. Hopefully the mechanical properties of this part will be better. Meaning it might be stronger and more resistance to compared to the original products. So that is one benefit you need to keep in mind when you design for something. When you design something for additive manufacturing, that is you could probably reduce the number of parts and eliminate the fasteners when you design some products for additive manufacturing. All right. And actually, there are other benefits for additive manufacturing when you do the design for additive manufacturing. First is the complex geometry, right? So you could design really complex shape, which can be manufactured using additive manufacturing, and customized geometry, right? Because the nature of additive manufacturing is kind of totally is different from those conventional manufacturing process. So to make the customized product will not be that expensive and difficult. Then you could consider about some customized shape instead of all the one for the mass production. And consolidated parts, just like the case we discussed over here, right? So you could merge the different parts to one part, as long as it can be additive manufactured. And so based on these advantages, you could have less constraints when you design your products, which can be additive manufactured. I mean, people used to have all those crazy designs, but the limitation is, although you can design some really nice product, but it cannot be manufactured using conventional manufacturing process. So if with the additive manufacturing, those constraints may not be there. So that's why it has little less constraints compared to the conventional manufacturing process when a designer think about some design idea. All right. So basically here show some examples. I think we talk a lot about it, so I just quickly go through them, right? And this one shows the integrated assemblies. And as I mentioned, this kind of motion can be achieved by printing some solutable support material and then wash away all these support, and then you have a motion, relative motion. All right. For example, the geometry like this, I would say it's really difficult to be machined, but using those metal print additive manufacturing process, this kind of part could be achieved. Right? So in terms of shape complexity, you can see some complex geometry like those lattice structures and all these animals with very complex features could be achieved using additive manufacturing, which are not achievable using conventional ones, right? And the complexity could be hierarchical. And I found this figure from a researcher, actually an assistant professor from Virginia Tech, and the researcher's name is Ryan Zheng. And basically, his major contribution is to develop a new method to generate those functional material using those hierarchical structures. Basically, in a small scale, you already have the structure like this, and these structure will repeat themselves to form a shape in larger scale. So basically, you have a hierarchy of the complexity over here. And that really gives you some unique material properties and which are not achievable when you are using some conventional manufacturing process. All right. If you are interested, you can check his work by search his name plus the Virginia tag. That's really there are a lot of impressive work over there, especially in the functional material area. All right. And also some functional complexity could be achieved, meaning instead of just material function, there could be some component function, like the case shown here. Basically, you could see additive manufactured like a small machine, right? And it's not just for the appearance. It's not a dummy shape. It has the motors, electronics devices, and also some laser over here. And it achieves those component functionality. It's not just for appearance. So that is another very uniqueness for additive manufacturing. Actually, I would like to talk about more along this line a little bit, based on one of my research work. Here shows another functional complexity example. Basically, this one's additive manufactured electronics devices integrated to some plastic or polymer substrate, right? As you can see, this kind of substrate is additive manufactured using the stereolithography-based method, and then the electronics components are placed, and the conductive ink are printed onto this substrate by some direct printing. Like, I mean, this kind of electronics printing is kind of they use the injection ink jetting based method to directly put all the conductive ink onto the object, and such that the electronic functionalities could be achieved. And there are some systems has such capabilities which can print those conductive ink there. One of the company is the Optomag, and it has several systems can do this work. Right, that is very interesting aspects for additive manufacturing. And of course, the multi-material, right? You could have material with different material property or even color, right? And also different translucence, right? Like the one shown here. So based on all the benefits from additive manufacturing, that researchers actually, they are trying to explore all the design freedoms by utilizing some of the benefits, like the part consolidation, consolidation and redesign, right? And utilize the hierarchical structures, and also come up with some customized design applications. And for example, this is a diesel. This is a diesel engine part, and you can see if the whole part is consolidated, and that will reduce the part number and the requirement for the assembly a lot. And the left one is the original design, and the right one is the redesigned model for additive manufacturing. So for the hierarchical structures, like what we discussed, the lattice structures, the truss structures, right? So when the researchers, when the designers have some design idea and some certain material properties is in desire, the designer could choose one of these structures and embed them in their design applications such that a certain material properties could be satisfied. And you can see here shows some examples, design examples by utilizing those octet truss structures in the design applications. And also those complexity could bring some good appearance, and the industry designers will utilize this kind of uniqueness to their design applications and to produce some really customized shape. What do they want? Another aspect of design for additive manufacturing is kind of optimization. So how to optimize your design based on certain requirement, and no matter how complex shape the optimization will generate, additive manufacturing could actually manufacture it. So that's the beauty where additive manufacturing could benefit. And as you can see here shows some bone structures. And you can see these kind of cellular or those hollowed shape is I would say it's the nature's design, and it actually is quite efficient and optimized. But for the structure like this, it used to be very difficult to be manufactured. And this one shows another example. If we check the bone structures for a human, and you can see all these features, hollowed features, gives you a lightweight and at the same time a very good mechanical properties. So it is more efficient to put the material in this way instead of just make a whole solid or some other artificial design. And then how to kind of learn from nature's design. We have some new method called generative modeling. Basically, those generative modeling will generate some optimized structure, and essentially, it is very similar to those nature's design, meaning the shape in those biomedical applications, right? And all those complex geometry can only be manufactured using the additive manufacturing. And but that brings a challenge for the computer-aided design software, because the computer-aided design software actually is developed for those conventional manufacturing process in a few decades before, right? So at that time, there's no way to manufacture complex shape or those biomimic shape. So what CAD can do well is kind of design those regular shape, which has those mechanical application. And how about those freeform shape or more complex geometry? These are very difficult to be modeled in conventional CAD software. The computational efficiency, the robustness, I would say, are quite unsatisfied. And but actually, people are working on it. Try to develop a new type of CAD software which are suitable for additive manufacturing. Also, the support from support for additive manufacturing will be converted to certain module in the new CAD softwares. But not only shape, the material property will be also a problem. Because we have the capability to precisely specify the material property in very basic unit, right? Unit, like the one we discussed in the last lecture, the HP additive manufacturing system. They use the voxel representation, meaning at each voxel they could do something. They could specify different material properties, right? But as we discussed, there's little support for the material property associated with the geometry representation. So these are very, I would say, urgent requirement for the computational tool. And also, once you have some unique shape, complex shape, how do you know what is the physical behavior, right? What do you know whether it satisfies your design intention in terms of functionality or the material properties or mechanical properties and so on and so forth. So that requires the physics-based simulation come in, right? It not just check the shape itself, but also the designed products need to be verified in terms of these more physical side of requirement. So all these are challenges for CAD softwares. And and also here shows a graded material, right? Basically, this is just a illustration, not meaning this brick is additive manufactured, but you can tell that you can see the concept of the graded material, right? So you could have softer material or stiffer material, and it can be manufactured in the same process, right? And which is quite different, quite difficult to be manufactured using the conventional ones. Actually, here shows a very interesting attempt to achieve the design system for those complex internal structures. So you have an original 3D shape, and instead of make this solid, a whole solid object, you could insert those patterns, those cellular patterns inside, right? And to efficiently and robustly compute the final shape. Basically, a new design system is developed, and user can control the patterns by specifying the dimensions, right? How many, what will be the smallest cellular size, and what will be the resolution, and so on and so forth. And after that, the system will automatically compute this final patterns for additive manufacturing. So the key is, it is not this is not based on the conventional computer-aided design software. It actually is some new software based on the new representation, which is more efficient and more robust. And that is the direction for the computational tools, to make the additive to make the modeling for and the simulation for additive manufacturing more efficient and more robust. All right. So we have toggled a few aspects of design for additive manufacturing, such as the complex shape modeling, and also some optimized design, optimized modeling for additive manufacturing. Also the functionality for additive manufacturing, right? So let's check a few work which related to all these aspects, such that you could have more idea about it. I saw someone, it seems someone messaged me, right? No? Okay. So any questions about this? We could have some discussion if you want on some aspects you feel interested. Anything? All right. Okay. Let's move on. Let me share another slide to you. So first of all, can you hear me still?
Yes.
Okay, I always have the illusion that I'm the only one. I'm talking to myself. That's the illusion I always have.
You are not alone.
Yeah. Okay. Just let me know if you're there. Okay. All right. So let's check some details instead of just some general information for the 3D modeling, optimization, and simulation. So as we mentioned, the slicing is the first step for an additive manufacturing process. And you can see a 3D model can be sliced into different layers. And in each layer, there will be the outer contour and also the infill, right? So let's check some details for the slicing algorithms, especially the one for the STL file, right? So basically, the slicing algorithm is doing the plane line segment intersections, right? So for each triangles, a slicing operation is to find out the intersection between the triangles with a z-plane. If we assume the printing direction is in z direction, right? So then the intersection will be the z will be the one with z-plane and also all the triangles, right? So basically, as shown in this figure, if that plane has an intersection curve with this 3D model, then we just store all the line segments in an ordered way. That means it forms a loop, right? And we do this for a set of z-plane with different height. Then we will have the different layers. And the height will be the layer thickness. So that's the concept for a slicing algorithms be performed on a triangular mesh surface, right? So as you can see, eventually you will have a contour over here. And in more detail about the plane triangle intersection. So for each vertices of a triangle, we need to compute a sine distance to the plane. If we represent the plane using this plane equation, right? And you can substitute each of the vertices of a triangle to this plane equation. Then you will have a d value, right? Actually, this d value has sign. And then there are different cases if you check each triangle edge, right? So there could be case if the 3 sine distance from the 3 vertices of the triangle to the plane, if they are all the same sine. That means there's no intersection, meaning this triangle is either on top of this plane or in bottom of this plane. So there's no intersection between this triangle and this plane. And another case is if there's one sine distance equals to 0, that means, okay, there will be one plane, the plane will intersect this triangle at one vertex. So you have one intersection in this case. But I would say the most common case is if there's an intersection is there are 2 intersections, meaning among the 3 distance from the 3 vertices to this plane, one of these distances have different sign with the rest 2. For example, in this case, if we check the specific this case, see, this is a plane. We use the 2D to illustrate the 3D case. And so the vertex 1 and the vertex 2, the distance for the 2 vertices, they are in the same sign. They're either positive or negative, but they are in the same sign. But the distance from vertex 3 to this plane has different sign with the D2, D1 and D2. So that means you have two intersections on this edge and this edge. Then you will have a line segment between these two intersections. And that will be one element in the whole intersected contour for your slicing result. So basically, that's how the how this intersection curve is computed. They just perform this kind of triangle plane intersection to all the vertices, to all the cutting plane, as well as to all the triangles. So can you guys suggest some possible problems for this plane triangle intersection? Any thoughts on this? What could be the problems?
Well, you end up with just all line. So it's a direction.
Beg your pardon, I didn't receive well. Can you repeat what you said? Hello?
Kevin's getting feedback. We're all getting feedback.
So you
Linear interpolation.
Oh, okay. Let me check what he typed. Let me check. Oh, microphone issue. That's fine. So you mean linear interpolation between what? I didn't quite get it.
So
yeah,
the model gets an irregularity in it because it's continually interpolating. Yeah.
Well, I didn't hear clearly, but yeah, there are some issues for your microphone or the network.
Yeah, I think it's everybody's microphone.
Oh, okay.
But one thing you could have
yeah,
2 or 3 of the vertices that are going to have Z0.
So the 3 vertices have what?
So right here now they all have 3 different cases. None of them is 0, 1 is 0, or different signs. But you could have 2 that are 0 or 3 that are 0.
Yeah, exactly. So basically, if the cutting plane intersect the triangle at the edge of the triangle, right? That could be one special case instead of just one intersection. For example, if this plane just goes through 1 to 2, then you will have a intersection on 1 to 2, right?
Mm.
You end up with a series of line segments. There will be some rounding. Exactly, the rounding error. I think Kevin raised a good point. Because we are doing the kind of numerical computation. So the rounding error sometimes will give you not just some inaccuracy, but also it gives you some logical error. That means if, let's see, for example, for this case, if the distance here gives you a very small negative number. It's very close to 0, but it's not 0, right? Then you could have a wrong judgment that basically this plane does not intersect with triangle, but actually it intersects. The only problem is when you do some numerical computation, those floating number computation, you will have the rounding error. You will have the numerical error. And sometimes this error will lead you a total wrong answer. And that is not solvable no matter how you improve your method, as long as you are still using the numerical computation, right? So that's a good point. And any other thoughts? Just imagine if you have very dense mesh. That means for the same shape, you could have a relative sparse mesh to represent the shape or you could have a very dense mesh, right? For many of the applications like those models with many small features, it could happen with the model has a lot of triangles over there. Then that will make this computation extremely slow, right? So sometimes it just takes infinity time to compute each of the layers. And another case happens if you want to have really small layer thickness. That means you will increase the number of your cutting plane a lot. And with the increasing of the cutting plane, then you will have more plane triangle intersection need to compute it. And again, that will slow down the whole process. So these are all issues for these plane triangle intersections. The numerical issue, the rounding errors, the density issue. If the mesh density becomes high, that will slow down your process. And also, if you have smaller depths, layer thickness, also the efficiency will be problem and the robustness will be problem. So that's why people are looking for some new representation, which is better than this triangular mesh representation, such that a more robust and efficient layer generation approach could be achieved. And but still, it's kind of an ongoing project. All right. Okay. I can see some. Okay. Let me see. Okay. The adjacent after slicing, the adjacent segments will not have common points. So the software needs to either pick one of the points or join them some way. Actually, what they did is they do a sorting. Yeah, you are right. They are not, if the computation is done separately for each of the triangle, then although the same, although for the neighboring segment, in terms of the position, they share the same nodes, but because you are doing the computation separately, so the algorithm will not know actually these two nodes are the same nodes. That's why people usually do a sorting after the line segmentation. I mean, this intersection computation. Again, that brings the problems. Brings the problems for the, because it still requires numerical computation. So that will lead you a wrong answer when there's some numerical error happens. Also, it is time consuming. Another possible solution, actually people actually are using that, is instead of computing the intersection per triangle, they are trying to utilize the connectivity of the triangles. So that means they know which triangle is connected to which ones. And when do the computation, they could figure out, okay, that node on that edge, that intersection nodes on that edge probably will also happen in the other triangle. Then they don't do the computation. They just save the computation in that way. But still, if the triangle quality is really bad, because what we're showing here, all the triangles are near to regular triangle, meaning each of the angle to be similar to 60 degrees. But if you imagine you have very narrow triangles or very flat triangles, well, that will really cause problems when you do the computation. For example, if you are computing a intersection between the plane to a very small edge, you can imagine how unstable it is. So all these problems will kind of somehow cause a problem, make the computation fail. And another fundamental problem for this method is if the triangle, the mesh with very bad triangulation, meaning it has problems. if there are some self-intersection, right? Some two triangles fold to each other, or there are some incorrect topology. Let's see, one edge linked to three triangles, which are, which is undesired for a CAD model, for a solid model. So all these things will cause this intersection, triangle intersection algorithm fail. So that's why people are thinking about to use the kind of implicit surface or those parametric surface to replace this triangulation representation. Are many different slicing algorithms used across the various AM commercial equipment manufacturing technologies, or is there a common favorable? I would say what I described here is the most commonly used one, the one based on the plane triangle intersection. Although there are some variations, like I mentioned, you could do the intersection separately for each triangle and then sort the line segment, or you compute based on the connectivity information. But the core is this, the plane triangle intersection. So they all suffer from the numerical, what are all the problems I mentioned. They suffer from that. And well, but I think there will be some new thing coming out to somehow solve this problem. I won't say solve it entirely, but kind of partially solve it. All right. Yeah, it's so fundamental. It's so easy to understand, but it's not an easy problem to solve. All right. Okay, let's move on. Okay, here shows what I mentioned last presentation, the step effect, right? So as you can see, the original surface is something like this, right? But when you do the slicing, you are actually using this kind of, in this case, in the 2D case, it's a rectangle to approximate the original region. So there will be some error happens here, right? Basically, there's nothing, right? The original, the bounding profile is something like this, but right now it becomes a zigzag shape. So that's the so-called step effect, and that brings the error for this slicing process. And try to solve these problems. One way is the adaptive slicing. So in contrast, there's a uniform slicing, which is the mostly used one. And the uniform slicing means you just put the layer thickness a constant value, right? And also you could varying the layer thickness based on the geometry. And what's the benefit to a adaptive slicing? The first thing is you could reduce the layer number. That means, like for example, in this one, this is quite typical, right? For this one, it has less. If you even make very thick layerness, if you make a very thick layer over here, still the approximation error is not that big. But in these regions with high curvature, you have to put more layers with smaller layer thickness, such that the approximation will be much better. And that is so-called the adaptive slicing. And this algorithm will consider about the actual shape of the 3D model instead of just blindly put the same layer thickness. I would like to stop here, and after 10 minutes, we just continue our discussion on this. All right?
Okay.
Yeah, we still have a few minutes. Let's start in 2 minutes. All right. Oh, okay. There's some discussion. Can anyone help Michael? Michael? He said, "Why is our echo so bad?" Can you guys help him?
So you have fine, but we
Oh,
hear your voice.
Oh, okay. Okay, let's start. So as I mentioned, there could be different slicing methods. One is uniform, another one is adaptive. So let's just imagine you have this. This is the 3D model. So if you have very large thickness, but same thickness, right? Then you have some layers in this way, and obviously it has a large approximation error. So the easiest way in your mind will be, how about we just decrease the thickness? We make the thickness even smaller. That means the layer number will become more, something like this, right? But the thing is, you have too many layers. You have a lot of layers. That will slow down both the layer, I mean the slicing algorithms and your actual additive manufacturing process. So another better idea is, how about we vary the layer thickness? At some place, we just have very large layer thickness. And for some of the high curvature area, we just have smaller layer thickness, such that the final layers will approximate the given geometry well. That is the thinking for the adaptive slicing. But unfortunately, this adaptive slicing is not that widely used, because if you make change to the layer thickness, that definitely increases the difficulty for your machine, right? especially the control strategy for your machine. And also to maintain the same accuracy will become more difficult if for the 3D, for the additive manufacturing system. So I don't see much of these systems actually utilize the layer thickness. So Clay asked, is layer thickness dependent only on feed head rate, feed head size? Would multiple feed head be needed to execute adapt slicing? Well, that's a good question. I think definitely one way to vary the thickness will be the size of a head. But also you could increase the feeding rate, right? Not just, I mean, even with the same printing head size, you could increase the feeding rate such that the larger thickness could be achieved. But still, it will change the current way of control for the machine. And that could bring some uncertainty. And I think that's the major reason for this kind of for the popularity of this kind of algorithms. Actually, the algorithm is there for a long time. Even in 2009 or something, there are some adaptive slicing algorithm there, but I don't know. Okay, so Kevin's suggesting for FDM, heating management with regard to getting good fusion between layers would be challenging. Yeah, that's another big issue. Exactly, the heat, not only the mechanical problems, but also the heat problems. Yeah, that could be another challenging. But I think, actually I have one thought, but I'm not sure whether it's okay or not. So how about those stereolithography based, SLA based? Do you guys, I mean, I want to hear from you. Do you guys think that kind of method will be a good scenario for this kind of slicing? Because for the SLA, you just need to, basically there's less heat over there. You just use the light source to cure the polymer, liquid polymers. So do you think it's possible to execute the adaptive slicing on SLA process? What could be the problems or challenges for the SLA?
So you're going to have to change how long the lasers actually attached to it, or hidden in place. And so that probably could give you all sorts of trouble with it trying to diffuse out in different areas. As far as how like your accuracy and how small of a feature you could really do.
Yeah, so you mean the laser size, right? Laser beam size.
Right. Because even if it's the same size spot,
yeah,
and you're holding it longer,
yeah,
it might be diffusing out further.
Okay, yeah, that's a point. And also, Kevin is asking that how would we vary the thickness of the layers? I think, yeah, the light intensity will be the way for us to manipulate this, and more energy applied, definitely the more material will be cured. But that, yeah, go ahead.
Let me ask you a question here. So they were trying to do this adaptive slicing.
Yeah.
But is it really that they're trying to print it with different thickness sizes, or they're just trying to reduce the computational overhead of performing the slicing operations?
I think the save is in both ways. So you have less layers, then you have less computation for the intersection, and also more importantly, they expect. I mean, the people who develop this algorithm are expecting to have better approximation in less layers. The uniform slicing can also achieve a good surface finishing as long as you have enough layers. But the thing is that will slow down your process, right? So how about we use less layer but achieve similar or better, even better shape approximation. That's the ultimate goal for this kind of adaptive slicing. Okay. Yeah, I think that must be a there are a lot of challenges when really implement this kind of algorithms. So you can see the gap between the people who are working in the design or computation area and the people working in the physical process and the machine design area. So, well.
Well, the other thing that is that with FDM,
yeah,
don't have square sides, more of a bead, and with the STL technology, you have more of a triangular slope. So even the technology doesn't give perfect rectangle.
Yeah. You mean the FDM machine cannot produce the perfect rectangle? Is it what you're suggesting?
Correct.
Yeah.
It's got a bend to it based off the film.
Yeah, definitely. I think you have a very good point. Basically, although in the computation it's a perfect triangle, but actually in the FDM process, the material near the boundary over here is not a perfect triangle, right? It's not a perfect triangle. So if the thickness become bigger, well, there must be some, I don't know, because I didn't test this this kind of adaptive slicing on my machine, but I assume that there will be some difficulty here to maintain the shape of a perfect triangle. So are your computer speak turned on? Yes, I think so there could be a course of the feedback. I don't know which speaker I'm using. I assume it's this one, but I don't know whether the computer's one is also. Okay, I don't know what I can do here. Can you hear? No, I cannot hear from with my earbud. I cannot hear myself. I can only hear you guys. Okay. All right. So what Doc suggests? Okay. So SLA depends on the size of power. Yeah. That's true. That's true. Yeah. All right. I mean, apparently there are a lot of restrictions for this kind of adaptive slicing to be realized. And well, maybe later on, if the printing efficiency for each layer becomes more and more efficient, we don't necessarily need the adaptive slicing, just to make a very fine layer thickness and then print them out. Maybe that's the solution. I don't know. Yeah, but we can keep on talking on this point. All right. So another step is the infill generation. So basically the infill is the filling patterns in the contour of the slicing. So that's the patterns inside the contour. And as you can see, there are a lot of different infill patterns, like those honeycombs, concentric, zigzags. I would say the zigzags is the most widely used ones. And well, people try different patterns, and these patterns could affect the material properties, the mechanical properties of the printed objects. And actually, there's some new some effort recently that trying to generate the optimized infill patterns using certain optimization algorithms, the topology optimization-based algorithms. So as you can see, the figure shown here, basically this is a work from Jun Wu, who's a assistant professor at TU Delft. Basically, he came up with the idea that utilizing the topology optimization tools plus the so-called principal stress line. So this one shows the principal stress line. and then generate the infill, something like this. And another contribution he made is, instead of generate a very sparse structure like this, he add on another constraint which is called the volume constraint. That makes you generate relatively dense patterns for each layer, because the infill could not be too sparse. Like this one definitely is not practical for the infill, but something like this or even this, I would say this one is quite good. Is reasonable density for additive manufacturing system to physically produce. And some results like this is achieved. So instead of using the experience of the designer themselves, this method try to let the computation tells what will be the shape of the structure is. So that's the, I would say that is the direction of the design go towards to. And let's see some videos. Let me share the video. All right. Okay. Let's check the video and we can have some discussion on this. All right. Let me share it. So can you guys see the video right now? Can you see the video?
Yeah.
Okay, good. So it's a very a short video. Basically, it gives you the how the algorithms optimize the shape. Basically, it starts with this basic design domain, and then the topology optimization will automatically generate these infill structures, and also with respect to the constraints of the loading and also the volume preserve constraint. All right, and you can see it's very similar to. Let me share back the. So as you can see, the final result is quite similar to the actual bone structure. It's quite like the bone structures, right? And well, that suggests that maybe our nature is a very good engineer, optimize all the structures in the nature creations. All right, so we can have some discussion. I can see someone typing. It looks like, oh, Kevin said, it looks like this is based on geometric density alone, correct? But for mechanical design, would a stress-based, well, it's not a geometric alone approach. Maybe I didn't explain well, but as you can see, this is a topology optimization. It's a finite element analysis is involved here. And as you can see here, these arrows, that gives you the loading direction. Basically, they modify the original topology optimization to make sure the generated structure will not be too small, too dense, too sparse. Because for the infill, you could not have some structure which is too sparse, right? You have to have certain density because it will support another layer on top of it. So that's why you have to add a volumes preserve constraints to the original topology optimization. All right. Okay, Clay said, do you know more about how the topology? Okay, that's a good question. Actually, I will introduce what is topology optimization in next few slides. I'm not sure whether right after this, but or some slides later. But definitely, I will give you the idea of a topology optimization. I talked to the idea to a lot of people, and they all love the idea. Okay, definitely, I will cover that. Okay, good. So let's move on. Maybe I just talk that part. because it's quite related to what we are looking at. All right. Let me talk about the topology optimization right away. Okay, can you see the slides with some result from topology optimization? Can you see?
Yes.
Okay, good. So basically, these are all applications of topology optimization, and you can see some of the structural topology optimization, like this one and this one. But some others, they consider about not just the structurality, but some like this fluid dynamics or this thermal effect. Basically, this is I would like to kind of explain this a little bit. So this is a customized arm cast. Why there are some hollowed structures? Because you all know those traditional cast, right? It's all solid, right? And it does not breathe. So it really causes the people uncomfortable. So that's why if we could put some hollowed patterns here, such that people, the heat can be emitted from those hollowed patterns, and that will give the patients who wear it a better experience. So then how to distribute these hollow patterns and what are the shapes and the size of these patterns? All of these questions need to be answered by certain topology optimization approach. So that's the story of this application. And also for this one, basically this is a valve from Tesla, and you have to optimize its shape, its topology shape by the fluid dynamics. It's not just a structural optimization. It needs to consider about the fluid dynamics. So these two are a little different from the the original structural optimization. All right. Okay. So also for the small scales, it's again from Ryan Zheng at Virginia Tech. The different structures could give you different material properties and give you some functional material modeling capabilities. And again, how to come up with these patterns and how to decide the size, the shape of these structures. It's still a very difficult problems. And those material people, they just, I would say, they utilize their experience, and they know what kind of structure or what kind of shape could give you what kind of material properties. But for other people, well, that's not possible for them to figure out how to design them, right? Even for the material scientist, it's still quite challenging problems by purely using their experience. So if there's some computational tool like the topology optimization or generative modeling tool, that will be a great help to them. And what is the topology optimization? So there's a definition I copied from the Siemens website. So topology optimization is a mathematical approach that optimizes material layout within a given design space for a given set of loads and boundary conditions such that the resulting layout meets a prescribed set of performance targets. So basically, the topology optimization starts with a given base domain. So, and the user could specify what will be the boundary condition and what will be the load they want. Then the algorithm will automatically generate, will grow the structure which satisfy the constraints and the requirements. So that is the working flow for topology optimization. And actually, that is a really exciting idea because from the perspective of cognition science, our human at most can only handle 5 variables when deal with certain design problems. But in the design applications, there are definitely scenarios more than 5 variables. Then how to come up with an optimal solution, right? There's no way to come up an optimal solution for human to use their brain to come up the idea. So that is why we need certain tool like the topology optimization tool to help a human to optimize their design. And as it's an algorithm, so there's no limitation on the number of the variables. So it could achieve something human can never think about it. So that is the beauty for topology optimization. All right, and let's check some good, nice applications. First of all, it achieves less weight, right? By minimizing the material consumption, you could better use your material. Only put the material where it's necessary, right? And sometimes it achieves even better mechanical properties by some simple design. Compared to some simple design. And sometimes the appearance could be a good point. Like it usually generates some organic like appearance for the optimized structures. So for the art piece and architectures, there could be some unique design, like the Qatar National Convention Center. The structure like this, it's quite unique and generated by these kind of topology optimization systems. And let's go through topology optimization a little bit. So here gives you the idea why people are talking about topology optimization with additive manufacturing. Because additive manufacturing can produce the products with very complex geometry. And at the same time, topology optimization will generate the complex geometry. So that will be a perfect marriage between topology optimization and additive manufacturing. One can generate a complex geometry. Another can produce the geometry to a physical object. Then that's a perfect match for them. So that's why both topology optimization and additive manufacturing are mentioned in the same time in recent research, all right? So let's check the working principle for topology optimization by going through this tallest problems. So let's see, we have a grid with the resolution 20 by 10. That means you have in total 200 those small grid over here. But we only have 6 Lego blocks. And each Lego block can be placed at only 1 grid. That means you need to find a pattern for the 6 Lego block on a grid with 200 grids. Definitely, that's an optimization problem. So one way to solve this problem is, okay, we just do the brute force. We try out every possible layout, but that's really heavy work to do. You can see how many possibilities for placing a 60 blocks onto a 200 grids. So this is a very huge number, and it's huge. It's too huge to be solved efficiently and practically. And we can check some possible patterns. Definitely, we could put all the Legos in a bar shape, right? Or some random shape like this, or some shape like this, right? Oh, another thing I forgot to mention is the obtained patterns of by placing the Legos will be the stiffest one. That means you have to have the stiffest structures by placing the 60 Lego blocks. And also a load will be applied over here. Yeah, these are boundary conditions and the restrictions, which I forgot to mention, right? So we have, we could random check these three possible designs, but which one's the optimal one? And with these three patterns, we could do FEA analysis to test out what is the structurality of the three patterns. And obviously, design A and design 2 has very poor structurality. You can see how large the deformation will be if you put the Lego in this way and apply the load over here. All right, but you can see for the design pattern C, there's almost no deformation. So it seems this one is the optimal one. But the question is how we find this solution, right? How we find this one by checking all the possibilities. So we come up with the idea of the topology optimization, and you can see the formulation here. So basically, this objective function is the so-called compliance energy. It measures how stiff or how soft of the structure is, right? And K is the stiffness matrix, U is the element strain, all right? And you put them together, that will give you the total compliance energy. And then we check the constraints. So first of all, we have this so-called static equation. Actually, this is the finite element. This is the equation which finite element method is trying to solve. And K is the global stiffness matrix, and U is the global displacement matrix, and F is the total load, the global load matrix. And by solving this, you will have the current displacement with current load applied. But you may ask, what is this one? What is the rho over here? Actually, rho is the so-called density parameters. So at each of the grid, there is a rho associated. And this rho gives you the idea that what is the density of the material at this grid. So 0 means basically there's no material. 1 means, okay, there are, at this grid, it is solid. So we could allow the rho to be varied from 0 to 1 such that we could have a density at each of the grid. And you can see here, we put the rho over here, and together with all the material properties like Young's modulus and Poisson ratio, we will have a different energy over here. And to solve this optimization problem, we actually find out a set of densities on each of the grid. And of course, because we set a rho a continuous variable, that means probably you could have some values at certain a certain grid to be like 0.005 or 0.3 or something like this. So to have a clear shape like this, we need to set up a threshold. Let's see if the density is less than 0.0001, then we just consider it as a hollowed grid. Otherwise, we think it is a solid grid. So by doing this, we will have all the material distributions on all the grid. And eventually, the result is this. is this one. So that is the concept of topology optimization. So anyone has any thoughts on this or questions? First of all, do you understand what I explained here? Okay, good. Yeah, I think it's good to talk about this problem in a very simple case, such that you will understand what the concept is. Good. Yeah, if you want to understand this fully, you have to go through the finite element method and also the mechanics classes, and especially those the elastic class mechanics classes, and to kind of get familiar with the strain, stress, and all the tensors for the strain and stress, and so on and so forth, such that you will have a kind of understanding in depth. But the basic concept, what I mentioned, is here. All right. So of course you need to consider about what will be the stiffness matrix and what will be the load, and put them together such that you could compute them. And here gives you a typical routine for topology optimization. And actually it is the an iteration. So first of all, you just specify the rho value to be 1 at all of the grids in your basic design domain. And then you just do the iteration step by step and update the rho, which is the density at each grid. That is why when you check the video, right, you can see a transition from the original base domain to the final pattern. So that is the iteration to update rho. And of course, you need to set up some kind of a convergency condition. Usually have if this rho does not change much, or the energy is less than certain value, or the energy, the change of energy is so small, it just means it converged, and this iteration could be stopped. So that's the kind of a basic routine for topology optimization. All right. So you can check some of the resources here. And one is the very famous paper from the Ole Sigmund at TU Denmark. And he wrote actually he's one of the founder of topology optimization method. And he has a few MATLAB code for the topology optimization available, which is very well written, very easy to follow. It's pretty good and very efficient. And also some freewares like the top-up applications. You could find the download from this link, and also the Inspire. I forgot to put here, but definitely Inspire is a very good, also very good software you could think about it. And some commercial ones, Tosca. Oh, actually, Inspire is. I'm not sure whether, but for student it is free. But I'm not sure how much it charges for other people. But definitely the Inspire and the Tosca from Dassault system are some very good and easy to use commercial softwares, and you guys can think about it. And actually, I'm working on a project related to topology optimization, and this project is related to this customized cost. And the idea is we are trying to use the 4D printing to manufacture it. Basically, this cost will be first made in a 2D pattern, and then by applying certain activation, then it becomes a 3D shape, like some possible way to change it to 3D is something like this. And that's a collaboration work between me and the University of Southern California. And what is method? Definitely you need to consider about the heat emission. So the thermodynamics will be considered in the topology optimization, and the comfortness will be also another consideration. At a certain point on the cost, it has to be reinforced. Then the load can be applied there. And so the solution will be the 2D pattern, which can be fabricated to a 3D shape through this 4D printing process. And actually, it's an ongoing project. I'm working on this surface flattening parameterization approach right now. Hopefully, I could generate something very soon. All right. So this is the topology optimization. And any thoughts, any comments on this? All right. I hope you guys have some basic understanding on topology optimization right now. Okay. Let's continue our discussion. I think we have very little time. Maybe I just talk a little more. Okay. I think you guys are quite familiar with the G code, right? So that is the basically that is the way to control the additive manufacturing systems, and all the tool paths will be converted to G code and control the machine. And maybe just skip the details. I think you guys are quite familiar with this. Okay, let's talk about the support material. So if this, so a typical way to identify whether a feature is overhanging or non-overhanging, you just need to consider about the angle over here. So it is bigger than 45 degrees. Probably you need to put the support material. Obviously, in this way, you definitely need to have the support material beneath the feature over here. So, but for different process, this threshold could be different. But a very widely used, I mean, typical use one is 45 degrees. And another thing to reduce the support material actually is the simple reorientation. If you have something like this, you just turn it by 90 degrees, so it's totally support free, right? So, I mean, for those novice users, a typical problem they make is they just do nothing before they apply, they press the printing button. They didn't check the orientation. They didn't check the possible problems for the geometry. They just blindly printed. So for the case like this, that is so easy to be solved by just rotate the model level, right? And here shows a kind of a test that if a different angle is put to this feature, what will happen? So as you can see, if this angle is, if you change the angle and make the facet, the normal of this facet more and more towards the ground, you can see how it gradually fill in the different angle, different cases, right? So if possible, you could modify this design feature that will effectively avoid the problems of support material. That is another example. Actually, I mentioned this before. See, this is the regular support material for fused deposition modeling. And these are some option ones. You can see these are like the branches of trees, right? And compared to the consumption of a support, the optimized one has much less one, right? much less support material requirement. And that is all because some optimization is applied here. But for this one, they just simply compute whether these features are overhangings, whether they require support. If the answer is yes, they just put the more than enough support over here. They just don't do any optimization over here. But this one, they kind of do an analysis, a load analysis, such that the support are added to the places where it's necessary. So you can see the big differences between the optimized one and this conventional one. And if you have interest, you could check this paper for details. All right. Actually, besides research, there are some commercial software. They also did some work like the mesh mixture. You can see they produce some support like this instead of the one generated by Cura. Cura generates the regular support material, but this one, mesh mixture, generates an optimal one. All right. Okay, I may stop here, and if you have some comments and questions, you can ask right now. All right. Anything? Okay, we can discuss more actually in the on-site session, and which is in the fourth week. Oh, I saw someone's typing. A little off topic, but will we be meeting next? No, I won't. We won't have a class next week. I will be in a trip next week because I have to present my paper at Texas A&M. So I'm sorry, sorry to have no class next week. But definitely from the fourth week we could discuss more. And yeah, all right. All right. To stick around after class now to help. Okay, yeah, thank you, Kevin. Let's figure out what's the problems. You can stay with me, and we do some tests to figure out what's the problem for the feedback, such that it could benefit to all the students. Okay. Yeah. If you guys have time, you could help me to figure out the problems. Okay. Let's do that. Let me stop the recording first. I think we don't need the recording anymore.